In this section, we're going to be computing the force exerted by a fluid on various surfaces. To begin, we need to start with some background. Suppose we have a column of fluid with cross-sectional area A containing a fluid with mass density ρ. This is the Greek letter ρ, which we're going to use for mass density of a fluid. So suppose we have this container of fluid. What is the pressure at the bottom, at depth D? Well, the pressure will be the weight of the fluid divided by the area of this base, which I'm calling A. What is the weight of the fluid? Well, it's the mass of the fluid times the acceleration due to gravity. This is either 32 feet per second squared if we're using imperial units, or 9.8 meters per second squared if we're using metric units. Okay, well, the mass of the fluid is just this mass density ρ times the volume V of the fluid. And the volume is the cross-sectional area of the base times the depth of the column. And so now I see that I can cancel this cross-sectional area A and simplify to just ρ dg. This is the mass density of the fluid times the depth times acceleration due to gravity. So this shows that the pressure at depth D is independent of the cross-sectional area. It's only dependent on the density of the fluid and the depth. So our conclusion of this calculation is that the pressure in a fluid with mass density ρ at depth D is ρ dg. Or if instead of mass density we're given a weight density, then we would not have to multiply by this acceleration due to gravity. It would just be that weight density delta times the depth d. Since we're going to be computing the total force exerted by a fluid on a surface area, it helps to have this formula in mind. If a constant pressure P is applied over a surface area A, then the total force applied to the area is the pressure times the area. In fact, we already used this in our earlier considerations. But the problem is, what if the pressure is not constant over the entire area? What if we're interested in an area which is not at just a single depth? Well, then we're going to divide the region into infinitesimal pieces which lie at constant depths. And we'll then use force equals pressure times area for these sections, and then we'll integrate. Okay, let's take a look at this example. A tank which is 8 meters by 4 meters by 2 meters contains kerosene weighing 820 kilograms per cubic meter to a depth of 1.5 meters. And we're supposed to find the force on the bottom of the tank and on one end of the tank. So first let's consider the force on the bottom of the tank. The bottom of the tank is at a single depth, namely 1.5 meters. And therefore, the force equals pressure times area formula applies. So we can simply plug in the known information. Remember that pressure we've already computed was ρ dg, the mass density times the depth times the acceleration due to gravity. And the area of the base was just, a rectangle, so it's just the length times the width, 8 meters times 4 meters. The height of the tank was irrelevant, right? It was just the depth of the fluid that was of interest here. That's why we have 1.5 meters here, and the 2 meters doesn't show up at all. Okay, what are the units? Well, if you multiply all these units together, then what happens? Here you have 1, 2, 3, 4 meters on top, and 3 meters on bottom. And so it looks like the units will be kilograms times meters over second squared. And if you remember, that's what newtons were. So this is 385,728 newtons of force on the bottom of the tank. Okay, so now let's do part B. Let's find the force on one end of the tank. So this is the vertical side of the tank. So here's a side view. The height of the tank is 2 meters. The depth of the fluid itself is 1.5 meters, and then this is 4 meters wide. And I want to compute the total force of this fluid exerted on this side of the tank. Well, since pressure is constant at fixed depths, we're going to divide this region into horizontal slices of infinitesimal width, and the pressure is constant there, so we can use force equals pressure times area for those slices, and then we'll integrate. So here's one of my slices, and I need some variable to specify the position of my slice, And I feel that the depth of the slice is a natural choice, and so I'm going to use the variable y to denote this, and here I've indicated that the slice is at a depth of y. The distance from the top of the fluid to the slice is y. I'm not using d because I'm going to have dy later on, and I would think it would be awkward to have dd instead of dy. Okay, so let's take a look at this. The force just on this slice is the pressure at the depth of the slice times the area of the slice, because the pressure is constant there. Okay, well, the pressure at depth y is rho times the depth times the acceleration due to gravity. And the area of the slice we'll now have to compute. Let's see, so the mass density was given, that was 820. The depth is variable, it's y for this particular slice. The acceleration due to gravity needs to be written there. And then the area of the slice is just 4 meters times the thickness, which is dy. Now, if this tank had been shaped differently, then the length of our slice would be variable, and we'd have to express that in terms of y as well. But we're lucky here, it's just a rectangle, so the length was just 4, that's constant. Okay, well, this is our expression for the force exerted on this area. I can simplify it, and here it is. But now we get to integrate this. The total force is that expression integrated from 0 to 1.5. The lowest depth was 0, and the highest depth was 1.5. And now this is an easy integral, which we can go ahead and do. Plug in the endpoints. If you plug in 0, you get 0, so you just plug in 1.5 here, and the answer was in newtons, as it was before. To recap, you're going to use the formula F equals pressure times area when you're at constant depths. When the pressure is constant, this formula applies. The pressure at a depth d in a fluid with mass density rho is rho times the depth times g. Or if you're given a weight density instead of a mass density, then you simply won't multiply by the acceleration due to gravity. So this is if they would tell you the fluid weighs some number of, say, pounds per cubic feet or something like this. Then you would not multiply by acceleration due to gravity, because pounds per cubic feet is a weight density rather than a mass density. Okay, in the next video we're going to be starting Chapter 7, which deals with differential equations. But this won't happen until after the second midterm, so for now, please try to answer this question. You're going to find the pressure experienced by a scuba diver who is 10 meters below the surface. And I do want you to ignore the pressure due to the weight of the atmosphere. Just find the pressure due to the water that lies above the scuba diver. And here's the important information that you'll need. And I want you to express your answers in units of pascals. That's the standard unit of pressure in metric. And it's defined to be 1 Newton per square meter.